This is a video about the Cauchy-Riemann equations, sometimes called the CR equations. And this will just be an introduction to what they are and how they work with an example or two. We're going to save the proof of the theorem regarding the Cauchy-Riemann equations for another video. So here's what we need to recall from Calculus 3. And specifically, we need to recall how do partial derivatives work. So let's take a function whose domain is the plane, or maybe some subset of the plane, and who spits out a real number. And let's let x0, y0, or x0, y0 just be a point in the plane. And again, I'm not talking about complex numbers now. We're thinking about Calculus 3. And let's define the following limit. And so here's the notation. And if you allow me to zoom in a little bit, it's like a curly d. That's like a partial derivative d that I'm sure you've seen before if you're watching the video on complex variables. So anyway, there's that curly df and then over curly dx. Usually you use the curly d when you have a function of multiple variables. And what we're going to define here, this is going to stand for the partial derivative of f with respect to the variable x at the specific ordered pair x0, y0. And what it should be is it's the limit as I let x tend to x0 of this difference quotient. And what I want you to notice about the difference quotient is the only thing that's changing here is x, right? X is moving towards x0. Notice it's y0 the whole time. And what you should take that to mean is that y is constant. And so we're going to call this the partial derivative of f with respect to x. And we'll say that you can take the partial derivative as long as this limit exists for the number x, or the point x0, y0 you're interested in. All right, so there's my partial derivative. And here's a way you should think about it. Like, what's it do? It measures the rate of change in the function f at that point in the direction, though, of the x-axis. And I'm going to draw you a little picture in a second. So when you think derivative, you might, for real numbers anyway, you're used to calculus 1 and thinking about, oh, it's the slope of the tangent line, it's the rate of the change in the function. But now when we're dealing with a function of two variables, there's lots of different directions that we could move in the plane. And so specifically, the partial derivative with respect to x is going to be the rate of change in the function along the x-axis, specifically along the unit vector, what we sometimes call E1 in like a linear algebra class, but just along the vector 1, 0. Think about 1, 0. So just like that sliver of the x-axis that goes from the origin over to the point 1, 0. That's what I'm thinking of E1 as. Of course, I'm kind of referencing like the standard basis along the x-axis here, if that makes you feel comfortable, if you've had some linear algebra recently. Let me try to draw you a picture about what on earth is this measuring, what's going on. So I've drawn you, and let me zoom in. I've drawn you this graph of this function that's in that teal color. Z is the function f of x, y. So there's its graph, and it's that bowl thing. You might call that a paraboloid if you remember. And what am I going to do? I've got this point that's on the graph, right? x0, y0. It's that purple point there. And what I'm going to do is I'm going to take this plane, P. And this plane, P, stands up vertically in the z direction, and it's parallel to the x-axis. Another way to say that is it's parallel to the xz plane. And this plane, I want you to imagine that plane that's dotted red there, cutting through the bowl so that it cuts through where that point is, that purple point is. And now what I want you to imagine that I tried to draw for you is, well, when the plane slices through the bowl at that point, it also is going to trace out a curve along where the bowl is. And so what the partial derivative does then, the partial derivative with respect to x is going to measure the slope of that curve. So again, we're kind of projecting down to some two-dimensional object to measure the slope, or projecting this onto a plane in order to measure the slope, just like we thought about a derivative in Calculus 1. So again, importantly here, this plane is parallel to the x-axis. It's really parallel to the xz plane. And I'm just going to think about what's that curve that it cuts out, and I'll measure the slope there. So the value of the partial derivative, that's what it's measuring geometrically. And let's do one more here. So let's look at the partial derivative with respect to y. And I'm going to call it that in a moment. And if you look, though, what's going on here? Now we're going to take the limit as y approaches the point y0 that I'm interested in. And I've still got this difference quotient, which is just the rate of change with difference in the outputs divided by the difference in the inputs. But now what I want you to notice is that y is changing, right? Y is approaching y0. On the other hand, now x0 is constant, right? It doesn't change. And so when you take the partial derivative with respect to y, that's when you hold x constant. And now, I didn't mention it above, I forgot to, but instead of this curly D notation for a partial derivative, another really common one that I'm probably going to use going forward, maybe interchangeably with this, is you put a little subscript in front of your function. So I put that little subscript y there. That denotes the partial derivative of the function with respect to y. All right, so then again, this limit is the partial derivative of f with respect to y, evaluated at that point x0, y0. And I've got another little blurb about how you should think of it. What does it do? It's a tool that measures the rate of change in the function at the point I'm interested in, but now I'm going in the direction of the y-axis. Specifically, what do I mean by in the direction of the y-axis? I mean, I'm measuring along the unit vector e2 that we commonly refer to the vector 0, 1 as e2 in like a linear algebra class. Or again, just think about you're on the y-axis and you go to the point 0, 1. Think about the vector that goes from the origin to that point. Boom, that's e2. I think I've got another little picture over here to try to imagine, or to try to visualize what's the partial derivative with respect to y. I've got my same function, and now what I'm trying to do, this one's a little bit harder. Imagine I take this plane now that stands straight up along the z-axis, right? But now it's parallel to the y-axis, and I want that plane to slice through the bowl. And where does it slice through the bowl at? I just want to make sure that it hits my point x0, y0. And what I want you to think about is that, well, when the plane slices through the bowl at the purple point, it's also going to trace out a little curve there. And so the partial derivative of the function with respect to y is going to be the slope of that curve again. Okay, so what can we say about partial derivatives from Calculus 3? Well, they enjoy a lot of the properties that the derivative from Calculus 1 enjoyed. And specifically, I mean that you get linearity. You can take sums and sums, differences, and constant multiples, and the derivative plays nice with those. You still got a product rule that works the same way, quotient rule, chain rule, all that good stuff. Okay, so we've got these partial derivatives in Calc 3, but we don't have like the derivative like we did in Calc 1, right? So far, like my notion of derivative that I've introduced so far, it depends on a direction. But what I need to do for complex, right? When I talked about a complex derivative a few videos ago, the complex derivative did not care about what direction you approach your point from. And so what we need to see is what's the connection between these partial derivatives from Calculus 3? How are they going to connect to define the complex derivative that doesn't depend on direction necessarily? All right, so I just wrote that down there. It doesn't depend on the direction that we approach our point from. So let's move on to the complex case. So let's let G be some subset of the complex plane. Specifically, though, that's a domain. And remember, domain, in the topological sense, is an open connected set. Let's let f be a function from G to C. Let's let z be x plus iy. And let's let the specific point z0 be x0 plus iy0. And so we're going to define the partial derivatives of this complex function with respect to each of its little component variables x and y in the exact same limit way above. So the exact same thing where the partial derivative with respect to x should just hold whatever y's you have constant, and the partial derivative with respect to y, you're going to do derivatives while holding x constant. So that's all I mean here. And I think I've got a little example, and just for emphasis, you hold y constant for df dx, etc. I've got a little example here. If your function is, say, z squared, let's think about that in terms of x's and y's. Remember, that's x plus iy squared. And if you FOIL that out, you should get x squared minus y squared plus 2ixy. And then now I can take the partial of this function with respect to x. You should see that you get 2x plus 2iy. Right, so like minus y squared would be 0 since y is constant. And similarly, the partial with respect to y, you should get minus 2y plus 2ix. So you might check that. Make sure you're following along with how to do partial derivatives. All right, so here's something cool that I want you to notice. Okay, what if I take, and so this is referencing this specific example, f of z is z squared, by the way. So what if we take our formula for df dy? So that's minus 2y plus 2ix up there. And here's what I'm going to do just randomly. I'm going to multiply by minus I. No rhyme or reason, just go with it. You're buckled in, you're sitting down, you're okay. We're going to multiply by minus I. And notice when you do that, distribute the minus I through there, you get 2x plus 2iy. Now go ahead and take a look. What was the partial derivative with respect to x up there? Oh, it's 2x plus 2iy. That's df dx. So what do we want to notice from this expression here? Somehow the two partial derivatives are related to each other. So here's a conjecture here. And it's not my personal conjecture. If f is a differentiable function, if it's differentiable at the complex number z0, then f should satisfy that little relationship. The partial with respect to x at z0 ought to be equal to minus I times the partial of f with respect to y at z0. So like any good mathematician, I do one example and I claim that it's true for all such functions. This is again a conjecture. I'm not saying it's true quite yet, but we're going to kind of dive into looking at is this relationship for real? And so we're going to prove it later. It turns out, yeah, it's for real, of course. Otherwise, why would I put it in a video? But before we do that, we need some better notation. Or maybe we need to get familiar with some of the other ways that we write functions of a complex variable. In particular, what we saw is that we can sometimes, it's nice to write a complex function f in terms of its real and imaginary components. So like a complex function has a real part and an imaginary part, just like a complex number does. And remember, you denote the real part by u, and so u is some function of xy. The point, though, is that u of xy is a real number, right, because it's a real value function. And similarly, v is the imaginary part of the function f. So, and I'm going to use my, nicer, in my opinion, notation for partial derivatives with the subscript. If I take the partial derivative with respect to x of this function, that should just be the partial of u with respect to x plus I times the partial of v with respect to x. And let's also do the partial of f with respect to y, which of course you would just do the partial of u with respect to y plus I times the partial of v with respect to y. Here I'm being a little bit lazy and I'm not including like the parentheses and inputs, right? So I'm just saying this holds for this function and should work for whatever inputs that you have. All right, so then now let's look at our relationship that we uncovered above in that one example that's related to our conjecture here. What if I take the partial with respect to y and I multiply it by iy? What does that do to u's and v's? And so if I take fy and I multiply it by negative I, and again, you can track through this, you should get vy minus iuy now. And so what we can do then is we're going to express this relationship in our conjecture again with respect to u's and v's. And so I'm saying that these two things should be the same. And so, okay, the left sides of the equations and the top are the same. And what we're going to get out of that is we're going to get a system that relates u's and v's to each other. And let me talk about where does this system comes from, just in case you can't see it. So where does this system I plopped down come from? All right, so I'm saying if the blues have to be the same, well, then that means I need to be able to compare the stuff that's in this pink square now, right? And I'm saying that those two complex numbers, ux plus ivx, and the other complex number, vy minus iuy, have to be the same also. But what's it mean for two complex numbers to be the same? Well, their real parts have to match, and their imaginary parts have to match. So I'm saying that the reds have to be the same, and the greens have to be the same. And that is where my little system comes from. Now, this system is super duper important. We're going to call this system, which again consists of two equations, partial of u with respect to x is equal to partial of u with respect to y, and the other equation is partial of partial of u with respect to y is equal to minus partial of u with respect to x. Notice I just moved the minus sign over. That's okay. That's how I personally like to write it. We're going to call this the Cauchy-Riemann equations. Ta-da, we've got them. All right, so then what's the big idea with the Cauchy-Riemann equations? Why are they cool? So far, what I'm trying to suggest to you is, with my one example, I'm trying to suggest that if your function's differentiable, then it satisfies these little equations. And so let's kind of set up what's going on, what's our usual setting when we're doing things. So let's let G be a domain in the complex plane. Remember, open connected set. Let's let Z0 be just some point in my domain. And let's let f be a function whose domain is G. And let's explicitly write out u and iv as its real and imaginary parts. So here's two things in this theorem. Really, there's like 2.5. Anyway, one, and this is what we talked about. If f is differentiable at Z0, then it satisfies the CR equations at Z0. Now here's the second thing, which is not as intuitive, and is actually a little bit harder to prove. Now, if we require a little bit more of our function f, if we require that the partial derivatives with respect to x and y are continuous in some disk centered at z0, so in other words, if I draw, there should be some little disk I can draw around z0, so that for all the little points in that disk, my functions fx and fy should be continuous. If that's the case, and if the CR equations hold at z0, then that's enough to say that f is differentiable at z0. And the last thing, I'll say a little bit more about these in a moment too, just to finish writing out the theorem. Let me zoom out a little bit too. The last thing is I can get a formula for what f prime looks like in terms of u's and v's and like partial derivatives. The derivative of the complex function f is the partial of u with respect to x plus I times the partial of v with respect to x. So that's a big deal. That's the big connection between, so the CR equations are the big deal because they're a connection between partial derivatives that I know about functions of multiple variables and how it connects to the derivative of a complex function. Now let's say a little bit about this theorem. So this says the CR equations are typically enough to check if f prime exists at the point you're interested in. And that's what number 2 means. And I underline this word typically, which is really vague. What does typically mean? So by typically, I mean in any intro to complex course, most of the functions you're going to deal with are going to have continuous partial derivatives around the point that you're interested in. So, if you were doing research on something, then that would probably be something you would need to check. But if you're just working an exercise from a book, most of those functions are pretty nice, that they typically satisfy too. So in that case, what I'm saying is, if your function is nice like that, then the CR equations are equivalent to being differentiable, right? They're characterizations of each other. It's kind of cool. All right, what else is going on here? What can we do with the CR equations? And the rest of the video is going to be more about what can we do. So the CR equations are going to help us find all points in the domain of the function where f is differentiable. And it's going to also help us find all points in the domain of the function where f is analytic. And it's also going to help us, this formula here, f prime, in terms of the partial derivatives, that can be useful for functions of a complex variable that's given to you explicitly in terms of x's and y's instead of just z's. So let's do an example that illustrates what's going on here. So here's this complex function z squared minus I times x squared. And of course here I'm assuming, right, that z is x plus iy like usual. So here's some questions that I want to answer, and I'll keep the questions in purple. So where is this function differentiable? All right, so if I write f as u plus iv, we should put it into that form. And so I'm going to get rid of the z, and I'm going to replace z squared by, I know z squared is x squared minus y squared plus 2ixy, so that minus yx squared. And now just regroup this so that you have the real stuff and the imaginary stuff together. And so what we see then is u is x squared minus y squared, and v is 2xy minus x squared. Now that I've identified those, it's time to play with the Cauchy-Riemann equations. And so what we're kind of doing is using like the contrapositive in a way of the CR equations, right? If we can find some spots where the CR equations don't hold, then your function's not differentiable there. Okay, by the way though, really it's I guess I should say in this example, this function's pretty nice because it's partial derivatives, right? You're just taking derivatives of polynomials, and you can take as many derivatives of polynomials as you want. Eventually get to 0. So in this case, the CR equations are actually going to be equivalent to being, the CR equations holding would be equivalent to the function being differentiable. Anyway though, let's get to the CR equations. How do we use them? So it's good to usually plop them down first. There's your system. And now that I've got an actual u and an actual v, let's take those partial derivatives. So when you take ux, that's 2x. And when you take vy, that would give you 2x also. So the first equation is 2x equals 2x. And in the bottom, when you take the partial of u with respect to y, that gives you a negative 2y. And when you take the partial of v with respect to x, that would give you 2y minus 2x. But then you've got to distribute the minus sign through. So I just change the signs. So I get minus 2y plus 2x over there on the right side. And what we're going to do is maybe simplify that system one more step of the way. Top equation is really 0 equals 0. Bottom equation is 0 equals 2x. And now I'm thinking, okay, how do I solve this system? Well, the top equation is always true. So any restrictions or constraints are going to come from the bottom equation, which of course forces x to be 0. So x has to be 0, but notice there's no conditions on y. Y is free to be any real number that you like. And if you think about, okay, what does that set look like where x is 0 and y can be whatever you like? That's the imaginary axis. And so what we just uncovered is that this function, right, along the imaginary axis, that is the only set of points where the CR equations hold. And so therefore, that means that this function is only differentiable for points that are on the imaginary axis. And I drew a little picture of the imaginary axis there, so just along the y-axis. Let's look at another question related to that same function. So where is this function holomorphic? And maybe up here that I use the word analytic, I see. Depending on what you might see, what book you use, analytic, we're going to use that interchangeably with holomorphic. And so for this question, I'll just keep it as holomorphic. Remember that meant it's got to be differentiable near the point you're interested in as well. So in other words, you should be able to draw a little disk around your point, some disk around your point. You should be able to get small enough so that the function is differentiable at the center and for every point inside the little disk as well. All right, so then where is this holomorphic? Well, think about the blue axis. Those are the only points where the function's derivative exists, but that's not a domain, right? Remember, domain is this loaded topological word that means open and connected. And well, if I took a point on the imaginary axis, like that pink point over there, and I draw any disk, of whatever small radius I like, it's always going to have points that are not on the line. It's always going to have points off the line. That's bad, right? That means it's not a domain. I can't draw a disk around that point such that the disk is contained in the set as well. Right? The disk will always have points off the line. Therefore, what we just showed is that this function is actually nowhere holomorphic. So even though the derivative exists along the imaginary axis, this function is not holomorphic or analytic anywhere. And the last thing we'll do, what is the actual formula for f prime? And here's where, just to show how to use it, we'll use this formula from the theorem. So the derivative of f ought to be the partial of u with respect to x plus I times the partial of v with respect to x. And when we do that, I don't care about a specific input z0, so we're just going to write generally what's the formula for the derivative. Well, we did this work above. I already know what ux looks like. It's 2x. And I already know what vx looks like. It's 2y minus 2x. And what else do we know? I only care about this. This formula only is valid when you're on the imaginary axis, which means that x has to be 0. And so if you just plug in 0 for the x's there, you're left with that the derivative has formula 2iy.